Alright, so today we're going to look at graphing rational functions. Like most topics in spring semester of pre-cal, you did this in Algebra 2. So it's not brand new. What I want us to do is to go very slowly over the parent function so that you've got a good foundational understanding, and then we'll pick up speed as we go through all the others. So our parent function is going to be f of x is equal to 1 over x. So remember, your parent function is your most basic function within a category of functions. And when we're talking about rational functions, the category that we're talking about is all of the functions that are ratios of two polynomials. So one polynomial over another polynomial. Okay? Basically, fractions of polynomials. So the most basic one is 1 over x. And we are going to start to gain an understanding of this function by looking at a very long table of values. Because we really want to see why this graph is doing what it's going to do. So I'm going to start with a very big number, 1,000. It's pretty big, right? As far as substituting into an equation. So my function is then 1 divided by 1,000. So to get a sense of how big that is, if I convert it to decimal, right, that's 0.001. So when my input was a pretty big number, because I'm dividing, my output was a pretty small number. See what happened there? Alright, so now let me jump down to like the number 10. If I input a 10, my output is 1/10, which is 0.1. So my input got drastically smaller, and my output got much larger, right? I mean, in money, this is 10 cents, and this is not even a penny, right? So what if I put in a 2? Then my output is 1/2. Or if I want to see the decimal, 0.5. Well, what if I put in a 1? Oh, that's easy. I've got 1 over 1, which is 1. But what if I put in a 1/2? So watch what happens here. My function says 1 divided by 1/2. So keeping in mind the definition of division, division means to multiply by the reciprocal. So that's 1 being multiplied by 2 over 1, which is 2. Well, what if I put in a 0?
That's where the asymptote will be.
That is where the asymptote is going to be. Why? What is my value of my function? How much is 1 divided by 0? Undefined. Remember, division by 0 is undefined. Undefined. That's the end of the word. So that is going to be a very important part of our graph, because that is going to be where there is a vertical asymptote. Alright, well, let's look at some of the negative values. So if I had negative 1/2, I would have 1 divided by negative 1/2, which would be 1 times negative 2 over 1, which would be negative 2. And then if I had a negative 1, I'd have 1 divided by negative 1, which would be a negative 1. And then if I had a negative 2, I'd have 1 divided by negative 2, or negative 0.5. And then you see if I put in a very small number, because the number negative 1,000 is actually a small number, right? I would get 1 over negative 1,000, which is negative 0.001, which is actually much bigger than 0.5. Because remember, on your negatives, this number is actually bigger. Alright, so you get a sense of what is going on with this function. So now let's go to the graph, and don't worry, we're not going to graph the thousands. But I wanted to put those into your table so you could see what was happening. So I'm gonna go 2 lines out and make that be 1, and negative 1, and 1, and negative 1. And we're going to graph some of these points. So I know that I have the ordered pair 1, 1. And I know that when x is 2, y is only 1/2. And I know that when x is 1/2, then y is 2. And so what happens is I get this curve, like so. But then, when x is negative 1, y is negative 1. When x is negative 1/2, y is negative 2. And when x is negative 2, y is negative 1/2. So then I have a curve over here. And so when we're dealing with rational functions, we are going to have graphs that have these different kind of branches to them. And they're going to have some curvature, and we're going to have some asymptotes. So our y-axis coming through here is a vertical asymptote. And this blue line is the line x equals 0. Right? It's a vertical line. Every point on the line has 0 for the x value. And again, it makes sense that our graph is not going to ever touch this blue line because division by 0 is undefined. So of course, when x is 0, I'm not going to have an output value. But there's another asymptote. There's a horizontal one. And in this case, it is at the y-axis. So I'm drawing my asymptote slightly above the y-axis just so that it's visible. But this is my horizontal asymptote. And it is the line y equals 0. Now if we go back to our function, right, it makes sense that this function is never going to have an output of 0 because this function is 1 divided by something. And 1 divided by something is never going to be 0. In order to equal 0, I would need to have a 0 on my numerator. And my numerator is the constant 1. So I'm never going to have a 0 on my numerator. So those are my 2 asymptotes. Now, we can also talk about end behavior with these rational functions. So as x goes towards infinity, the limit of f of x, so as x goes out to the right, what is my output getting closer and closer to as I go out here?
0.
0. Then I can talk about my end behavior over here. As x goes out towards negative infinity, the limit of our function. So as x goes out this way, my output gets closer and closer to 0 also. Now, right here, this is not end behavior, but I can still describe it with limit notation. Because right here, I'm talking about as x approaches 0 from the positive side. So 0 with a little plus sign up there. So that means as I go towards 0 from the positive side, my function goes where?
It approaches infinity.
It approaches infinity. But I can also describe what's happening over here. So over here means as x goes towards 0 from the negative side, the limit of my function goes towards negative infinity. All right. Another thing we want to talk about with rational functions always is domain restrictions. So our domain has a restriction here because we cannot divide by 0. So my domain is a set of all x's such that x is an element of the real numbers, but x cannot be 0. So there's going to be a relationship between our restricted domain and our vertical asymptote. All right, and I'm going to take a pause there. All right, so we are going to now look at how do we know where the vertical asymptotes are. So if I have a function f of x, and it's a rational function, which means it's one polynomial over the other, and I'm just going to write my polynomials in a general form. A sub n times x to the nth power plus blah, 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 right? Over b sub m times x to the m power plus blah, blah, blah. So whatever else you're adding and subtracting to your function, what we really care about is the degree, right? So n and m are the degrees, right? They're the degrees of the numerator and the degree of the denominator. And then the a sub n and the b sub n, those are the leading coefficients. And so when you're trying to determine what your horizontal asymptotes are, those are the only items you have to worry about. Whatever the other stuff says is not going to affect the horizontal asymptote. So what you want to do is you want to find n and m and you want to compare them to each other. And then you have three situations. We have if n is less than m. We have if n is equal to m. And then we're going to have if n is bigger than m, greater than m. Right? Those are the three possibilities. So if the degree of your numerator is smaller than the degree of your denominator, then horizontal asymptote, I'm just going to put capital H, capital A. For horizontal asymptote, y equals 0. So the function that we just did was an example of that. The degree on my numerator is actually x to the 0 power. The degree on my denominator is x to the first power. 0 is less than 1. And we had a horizontal asymptote at y equals 0. Right? That's all that's saying. If your degrees are equal to each other, so let's say you had a third power over a third power, then the horizontal asymptote is going to be y equals the leading coefficients over each other. Sorry, this should be b sub m up here. I made a mistake. So these are my two leading coefficients. Just to remind you, that's what those guys are. And so we're going to do an example that has one of those in a minute. Now, the other situation is if your numerator degree is higher than your denominator degree. So like if you had a third power up top and only a second power on the bottom, in that case, then no horizontal asymptote at all. So those are our three scenarios. All right, so let's do an example together. That's not the parent function. So we're going to take g of x is equal to 3x cubed minus 3 divided by x squared minus 9. And we want to find our domain and our asymptotes and our intercepts, and we want to graph it. Like we're going to do a whole bunch of stuff with this function. The first thing we want to do before we do anything else is to factor. So on my numerator, I see that there's a common factor of 3. So I'm going to start by factoring out a 3. And on my denominator, I see that I have the difference of two squares. So I'm going to factor that into x plus 3 times x minus 3. And then on my numerator, I'm going to say, wait, I can factor that even more because that's the difference of two squares. So I'm going to break my numerator down into 3 times x plus 1 times x minus 1, and then my denominator is going to stay x plus 3 times x minus 3. Alright, let's start with the domain. And so for your domain, we have to figure out what are the things that x cannot be. Right? We cannot divide by 0. So therefore, neither of these two factors can be 0. So x plus 3 cannot be 0. X minus 3 cannot be 0. So that means x cannot be a negative 3, and x cannot be a positive 3. So I will write out my domain as a set that restricts those values from being included. X, such that x is an element of the real numbers, but x does not equal negative 3 or 3. And this same information is going to tell me my vertical asymptotes. So I'm going to have a vertical asymptote on x equals -3, and I'm going to have a vertical asymptote on x equals +3. So now let me consider horizontal asymptotes. Well, let's look at my degrees. My degree on my numerator is the third degree. My degree on my denominator is a 2. No. Oh my goodness. This is supposed to be a 2. Was anybody looking at that confused how I went over here? I just saw too many 3's. So let's just back up. That's 3x squared. So when I factor out the 3, it was 3 times x squared. So my degrees are actually 2 over 2. So that means my n and my m, my 2 degrees, they're equal to each other. So when we have that situation, our horizontal asymptote is going to be y equals, and it's going to be the leading coefficients. So my leading coefficient here is 3, and my leading coefficient on my denominator is a 1. So that's just y equals 3. Alright, so I'm going to take the parts that I know and graph. I'm going to come in here and make a thingy, coordinate plane. I'm going to go out to 3. I'm going to go out to -3. I'm going to grab my blue pen and make vertical asymptotes. I'm going to go up to y equals 3. I'm going to grab my green pen and make my horizontal asymptote. Alright, y equals 3, right there. This is x equals 3. This is x equals -3. So now I've kind of got my coordinate plane divided into these sections, and I know I'm going to have these curves, and I know that they're never going to touch the green and blue lines, but I kind of need to figure out where they are. So if I figure out my intercepts, so my x-intercept happens when y equals 0, or when g of x equals 0. So remember, my g of x was 3x squared minus 3 over x squared minus 9. So all I need to worry about is that if my numerator is 0, does it matter what I'm dividing by? 0 divided by 7, 0. 0 divided by 100, 0. 0 divided by 5,649, 0. So if this top part is 0, then I'm on 0, right? So where is my top part going to be 0? Let me look back to my factored form. My top part is going to be 0 at -1 and +1. So those are my x-intercepts. Now what about my y-intercept? A y-intercept happens when x equals 0. So just go to your function and put a 0 here. If this is 0, then all this part is 0. And if this is 0, 0 squared is 0. So if these two parts are 0, what do I get? -3 over -9. Negative divided by a negative is positive. So that would be +1/3. So that's my y-intercept. So on 0, I'm at like 1/3. So those 3 points there give me enough information to know that I'm curving like this. But there can be some more stuff happening. So let me try and plug in the number 4, right? Because that's past here. So if I plug in a 4, well, let me plug it in the factor form. I think that's easier. So I'm going to have 3 times 4 plus 1 is 5. 4 minus 1 is 3. 4 plus 3 is 7. 4 minus 3 is 1. So that's going to be 45 over 7. It's going to be a little over 6. So at 4, I'm at 3, 4, 5, 6. A little higher than 6. That's enough to just tell me that this guy's coming in like this. Just needed to know that it was up in this section and not down here, right? So you don't have to be very specific with your curve, as long as you know which section to put it in. So then over here, what if this is a -4? So again, I'm just going to come up here and substitute, do a little mental math. 3, -4 plus 1 is -3. -4 minus 1 is -5. So that's going to be positive 45. And -4 plus 3, -1. And -4 minus 3, -7. Negative times a negative, that's a positive. So that's also going to be up there around here. And so you're going to go like that. Alright, so the assignment with this is page 138, numbers 1 through 15 odds, and the answers are on page R52, and you can look that up on your online textbook, McGraw-Hill.